Welcome to Electrical Circuit Analysis. Throughout this tutorial, I'd like to request you to pause this video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate your understanding. In this tutorial, we're going to talk about basic circuit variables such as current, voltage, power, and basic circuit elements such as resistors, capacitors, inductors, voltage sources, and current sources. Charge arises from the electrical property of the atomic particles of a material. The unit of charge is coulomb. Current is basically the rate of change of charge with respect to time measured in amperes. The relationship between charge and current is shown in the equation on the left here. Here Q is charge and I is current, and I equals dq dt means that the current is equal to the rate of change of charge with respect to time. Conversely, if we know the current and we're trying to determine the amount of charge that flows during a time period, that is Q, we integrate both sides of the equation on the left with respect to time. If we do that, we get the equation on the right here. Q equals integral I dt. So the current I, the amount of charge that flows between times t0 and t, can be determined using this equation. If the value of current does not change with time, it is called direct current or DC current, as shown in the left here. And if the current varies sinusoidally with time, as shown in the right here, it is called alternating current or AC. So for AC current, the current value starts from 0, then goes to a positive maximum, then it comes back to 0 and goes to a negative minimum, and then it comes back to 0 again, and the cycle continues. In an electrical circuit, we can reverse the direction of current, provided that we also change the sign of the magnitude of the current. So in the example here, on the left figure, 5 ampere current is going from bottom to top. This is equivalent to say that minus 5 ampere current is going from top to bottom in the same way. In other words, a negative current of minus 5 ampere flowing in one direction is the same as a current of positive 5 ampere flowing in the opposite direction. Thus we can reverse the direction of current provided that we also change the sign of the magnitude of the current. Okay, so now here is a problem to test your knowledge. Please pause this video and try to solve this problem, and then we'll match our answers. Okay, so hopefully you've been able to solve this problem. So here the charge is given, an expression of charge is given, and we need to determine the current at a particular time point. So as we know, the relationship between current and charge is I equals dq dt. So basically we differentiate this function with respect to time, and we get the equation of current, and then we put t equals to 0.5 seconds in this equation to obtain the current value at 0.5 seconds. Okay, so here is another problem. So please pause this video and try to solve this problem, and then we'll match our answers. So hopefully you've been able to solve this problem. Basically here the equation of current is given. We need to determine the charge that is passing between t equals to 1 second and 2 seconds. So as we know, Q equals the integral I dt, and the limit of the integral will be from 1 to 2 because we're trying to determine the charge that passes from 1 to 2 seconds. And then we perform the integration and put the limit to obtain the charge that passes between 1 to 2 seconds. Okay, now we're going to talk about voltage. So the voltage between 2 points A and B in an electrical circuit is the energy or work needed to move a unit charge from A to B. So therefore the voltage equals rate of change of energy, W here, with respect to charge, Q here, and the unit is joule per coulomb, which is also commonly referred to as volt. So the plus and minus signs here are used to define reference direction or voltage polarity. So this can be interpreted in two ways here. So here the polarity sign here, plus and minus, at point A and point B respectively, can be interpreted as point A is at VAB potential or VAB volts higher than point B. So point A here is at a potential of VAB volts higher than point B. Or the second way of interpreting is that the potential of point A with respect to point B is VAB. So, I mean, either way it's the same thing. So it's just how you see it. You can consider VAB here and the polarity sign here as the potential of this point with respect to this point, or you can consider it that if the voltage at point B is 10 volt, the voltage at point A will be VAB plus 10 volt. So, yep. Just as we were able to reverse the direction of current provided that we also change the polarity of the magnitude of the current, we can do something similar to voltage as well. So in an electrical circuit, we can reverse the polarity of voltage provided that we also change the sign of the magnitude of the voltage. So in figure A, VAB is equal to 9 volts, and in figure B we have reversed the voltage polarity, and therefore we have added a minus sign to compensate for that. Thus we can reverse the polarity of voltage provided that we also change the sign of the magnitude of the voltage. Please also keep in mind that the electric current is always through an element, and electric voltage is always across the element or between 2 points in a circuit. Okay, so the definition of power is the time rate of absorbing or delivering energy, and the unit of power is watts. So power is equals to rate of change of energy. W here is energy, so P is equals to dW dt. Power can also be computed simply by multiplying the voltage and current of an element. So another important principle is that the total power supplied to the circuit must balance the total power absorbed. So in other words, if the circuit generates 100 watt power, it must also consume 100 watt power so that the total power of the circuit sums to 0. So this idea basically comes from the energy conservation principle, that you cannot store the power in a resistive network. Therefore, the amount of power generated is equal to the amount of power absorbed. Again, if we know the expression of the power, how then do we determine the energy consumed or generated in a time period? So if we integrate this equation with respect to time, we get the equation of energy, W equals to integral P dt. And the electrical power utility companies measure energy in watt hours. So if you run a 1 watt bulb for 1 hour, it will consume 1 watt hour, or 3,600 joules of energy. Therefore, 1 watt hour is equal to 3,600 joules. Okay, so now we're going to discuss how do we determine if an element in a circuit is generating or absorbing power. So the first step is to find the voltage and current of that element, considering that current flows into the positive terminal and leaves the negative terminal. So this is our model example here. So in this element, in this circuit element, current is entering through the positive terminal. So when we're trying to determine whether or not an element is generating or absorbing power, we will bring the current of that element in this format, that is entering through the positive terminal. Now you might ask, what if the current is leaving through the positive terminal? Then what we're going to do is that we're going to reverse the current direction and change the polarity sign here. So we just learned a little while back that we can reverse the direction of a current provided that we also change the sign of the magnitude of the current. So if, for instance, in a circuit element the current is actually going out of the positive terminal, we're going to reverse the direction of the current so that we have the direction of the current and the voltage polarity in this exact same format. Next, we simply compute the power. Power is equals to voltage times current. And if the power is positive, then the element is absorbing power from the circuit. And if the power is negative, then the element is delivering power from the circuit. So these are the simple two steps that will help us to determine whether or not an element is generating or absorbing power in a circuit. So let's illustrate this with an example. So here we see that the current of this element, through this element actually, is going out of the positive terminal. So that's not according to our format. So what we need to do is that we need to reverse the direction of the current. So in the figure on the right here, I have reversed the direction of the current and also added a minus sign in front of the magnitude of the current. Now this follows our format. Now a current is entering through the positive terminal of this circuit element. What we're going to do now is we're just going to multiply this value with this value. So we get minus 12 watts, and this is a negative number. We don't look into the magnitude, we look into the sign of the power. So if the sign is negative, then the element is generating or supplying power to the circuit, and the sign is positive, then the element is absorbing or consuming power from the circuit. So in this instance, the power is negative, so this element is supplying 12 watts to the circuit. So now please pause this video and think about these three problems and try to figure out whether the circuit elements in figure A, B, and C are generating and absorbing power from the circuit. So please write down your answer and then we'll match. Okay, so hopefully you've been able to solve this problem. So here the current is entering to the negative terminal. The current goes through this element and goes out of the positive terminal. So that's not following our format. We want the current to go through the positive terminal, which means we need to reverse the direction of the current. So if 3 ampere current is going out of the positive terminal, minus 3 ampere current is going in, and then if we just multiply the minus 3 times 4, we get minus 12, which means the element in figure A is supplying power to the circuit. Okay, let's go to figure B here. Here, current is going out of the negative terminal, which means it came through the positive terminal. Otherwise, there is no way it can go out of the negative terminal. So this is actually following our format, so we don't have to change anything. We just multiply 3 ampere times 4 volt. We get 12 watts, which is a positive number. That is why this element is absorbing power from the circuit. Okay, let's go to the circuit element at C here. So here we see that it's exactly following our format. That is, the current is entering through the positive terminal, which means we don't have to do anything. We just multiply current and the voltage to obtain 12 watts, which is a positive number, that means this element is absorbing power from the circuit. So hopefully this is clear to you. So now we're going to talk about some common circuit elements. So we can divide circuit elements into two categories: active elements and passive elements. In general, active elements generate energy or supply power to the circuit. Examples of active elements are batteries and generators, and voltage sources and current sources. On the other hand, passive elements are elements that consumes elements from the circuit. Consumes power from the circuit. So some of the examples of passive elements are resistors, capacitors, and inductors. So here are some of the common examples of passive elements, and basically symbols of passive elements. So this is a symbol of resistor, this is a symbol of capacitor, this is a symbol of a capacitor, but its capacitance is not constant, and this is the symbol of an inductor. Okay, now we actually do not call active elements active elements. We refer to them as sources, voltage sources or current sources. So voltage sources basically maintains a certain voltage across the terminals, and current sources basically gives a certain amount of current to the circuit. So voltage or current sources can be further subdivided into two categories: independent sources and dependent sources. So independent sources are sources whose voltage and current are completely independent of other circuit elements. So if it's a 5-volt voltage source, it's always going to maintain 5 volt across its terminals. Again, if it's a 10 ampere current source, it's always going to supply 10 ampere current no matter where you connect it. Okay, so another category of voltage or current sources is dependent sources, whose voltage and current are dependent on other elements of the circuit. So the voltage and current values of dependent sources are not fixed numbers. It's basically a variable, and the variable is basically a voltage or current of another element of the circuit. So dependent sources can further be subdivided into 4 categories. So these 4 categories are voltage control voltage source, current control voltage source, current control current source, and voltage control current source. Excuse me. So we can see that the first 2 categories are voltage sources, but the first dependent voltage source here, this box here, is controlled by the voltage of another element in the circuit. And the second voltage source here, the second box here, is controlled by the current of another element in the circuit. So they are called voltage control voltage source and current control voltage source, respectively. We can see that the last 2 categories are current sources, this one and this one. But the first dependent current source here is controlled by the current of another element in the circuit, and the second dependent current source here is controlled by the voltage of another element in the circuit. So they are called current control current source and voltage control current source, respectively. So these are the 4 types of dependent sources. Now we're going to look into some of the symbols of those voltage and current sources. So both of these are symbols of independent voltage sources, but we're going to use this. This is most commonly used because and this one on the right here is the symbol of an independent current source. So basically the value of the current source and an arrow mark here. So these are the symbols of the 4 dependent sources that we just discussed. So this is the symbol of voltage control voltage source. This is a symbol of voltage control current control voltage source. and this is current control current source, and this is voltage control current source. So in order to identify whether or not an element or a source is a voltage source, you look into the you look inside this diamond shape. So if it's a diamond shaped source, then it has to be a dependent source. And if it's a circular source, it has to be an independent source. And if there is a polarity sign here, plus and minus sign, that's a voltage source. And if there is an arrow sign inside, that should be a current source. So this is from this diamond shape, we understand that this is a dependent source. And from this polarity, we figure out that, okay, this is a voltage source. So this is a dependent voltage source. Now, how do we know it's a voltage controlled voltage source? So we look into the variable here. If it's a V something, V0, V1, Vx, so if it's a voltage, then it is a voltage controlled voltage source. But if it looks like a current, for instance here 10I, where I is like a current of another portion of the circuit. Again, from this diamond shaped structure, and this arrow here, we understand that it's a dependent current source. And since it's I here, which is a current of some part of the circuit, which means it's a current control current source. And for Vx by 4 here, Vx is voltage of some part of the circuit, which is why it's a voltage control current source. Now we need to keep in mind one important thing, is that a voltage source, be it dependent or independent, keeps the voltage constant. The current could be anything. Also, a current source, be it dependent or independent, keeps the current constant. The voltage across the current source could be anything. Okay, now please pause the video and try to solve the problem, and then we're going to match our answers. Okay, so hopefully you've reached this answer. Okay, now please again pause this video and try to solve this problem, and then we'll match our answers. So hopefully you've been able to solve this problem.